Now consider more general setting where there is no central node. In the previous example, we have one central prompter server which combine all the information and then broadcast the combined information to each local machine. Okay, so in that case, there are huge communication between central server and all the local servers. And also we have to have some synchronized or well-designed network. Okay. More general scenario, like this figure, when we don't have such central server, we have to communicate totally in local way. So when we don't have any prompter server, we have to construct such a mesh network, and purely local communication only exists. At each time, instead of combining all information to one single central server, no, we just communicate with the neighbor node. So here neighbor node is all the nodes connected, directly connected to the target node. Okay, so for instance, in this case, this node has two neighbor nodes, and this node has three neighbor nodes. And after each gradient computation, each node can communicate with its neighbor, but they do not combine one single global information using the communication. Okay? Then how can we learn from this scenario? So there are a bunch of researches how to solve such distributed setting. For instance, plain decentralized SGD algorithm is one possible solution. So this algorithm utilizes Kashib algorithm, and Kashib algorithm was invented very long times ago to deal with such totally decentralized environment. So when you look at the pseudocode, the algorithm is very simple. At each time, each local machine computes its own stochastic gradient based on their data point, and then partially update their parameter first. So why I say partially, this is the end of one iteration, because so after update their parameter, only use their own data point using stochastic gradient. They send all the nodes, they send the updated information to their neighbors. Of course, the node also receives some message from neighbors. So send and receive message from neighbors and to neighbors. And each node update their parameter value based on their own parameter and also the neighbor's parameter. Okay, so it controls Wij control how much weight you consider its local information and the neighbor information. So here I wanna use W, the capital W, to denote the weight matrix, which consists of Wij value. We usually consider a very symmetric case, so when you set Wij equal to 1, then Wji as well. So we consider a very symmetric weight matrix. And also we consider weight matrix of which largest singular value equal to 1. Okay, let's say S1W is the largest singular value, then it should be equal to 1. And from the second largest singular value, it should be strictly less than 1. Okay. And also we consider the weight matrix where the weight value is not equal to 0 if and only if there is connection between them. Okay, so in the previous figure, because these two nodes has connections between them, we have a non-zero Wij value. But between these two nodes, because there is no connection in the figure, our Wij value, the corresponding Wij value, must be 0, according to the rule of W matrix. Okay? So we will use such W matrix for this algorithm. Then we have very nice property. Okay? And also we want to set W matrix so that it has all one vector as eigenvector, of which eigenvalue equal to 1. And because since W is symmetric matrix and real valued, so the eigenvalue is essentially singular value when the eigenvalue is positive. And because the eigenvalue of this case is equal to 1 and the largest singular value is equal to 1, the all one vector essentially is a singular vector as well, and the corresponding singular value is the largest singular value. Okay, so all one vector is the largest singular vector. So these properties are very nice. Why? So when you multiply xt plus 1, so from let's say from any initial point x0, when you iteratively multiply the W matrix to Wt, then Wt converges to, when t goes to infinity, where it converges to this all one vector transpose times x0. Okay, times 1 over n. Why? It is because the W matrix contain when you iteratively multiply W matrix, since we know that the largest singular value is equal to 1, and all the other singular values are strictly less than 1, which make only the all one vector direction can keep the length during this iterative multiplication, but all the other directions information converges to 0. The magnitude of all the other direction converges to 0 because you multiply less than 1 value iteratively. So when you learn this matrix multiplication infinitely many times, then your vector will converge to here. And since 1 times 1 transpose matrix of which singular value is n, so you have to normalize 1 over n. Right? So essentially the true singular vector, the normalized singular vector is 1 over square root n times all one vector. And because this is so this is the solution when you compute this when t goes to infinity. Okay. So the W matrix has very nice property like this. And what is the physical meaning of this? What is physical meaning of this? What is the physical meaning of 1 times 1 transpose times x0 vector times 1 over n? This is the average vector. when you compute this matrix, all the element is the empirical average, or just average over whole element value at time 0. Okay, x1 plus x2 plus up to xn at initial time over n is the final result. So when you multiply W matrix that satisfy all these properties, then essentially this matrix multiplication process in the end contain the consensus, the average value. Okay, that is why we communicate with this W matrix, with this W weight. This plain decentralized SGD algorithm essentially trying to implement some empirical average between all the nodes in the network using this W matrix multiplication. Okay, so when you learn this plain decentralized SGD algorithm infinitely many iterations, in the end all the servers will share the same parameters from this W multiplication. But the problem here is in this case we simply multiply W matrix and starting from the x0. But this algorithm, in the middle, we really change the xi value by using the gradient, stochastic gradient, locally. Okay, so the xt is not simply w per t times x0, because every time you move a little bit, every time you have xt plus 1/2, you have half iteration update here. So actually this does not hold for this pseudocode. So here we introduce another very interesting idea we have to introduce. This is called Choco SGD algorithm. Okay, the Choco SGD algorithm has this Tungrat QSGD idea, and also there is a very important and interesting idea. So basically we have eta t step size for this stochastic gradient, but also we have another step size gamma here. Okay, we update xit plus 1/2 plus gamma times the Gaussian algorithm update, W matrix multiplication. Okay, so when you ignore the quantization error, this is equal to 1 minus gamma xi plus 1/2 plus gamma times wij xj t plus 1/2. So this part is exactly the Gaussian plain decentralized method, and the gamma basically control the speed of decentralized method. Okay, so this gamma make your W matrix to 1 minus gamma identity matrix plus gamma W matrix. Okay, which control the conversion speed of decentralized algorithm to the average. Okay, And the gamma, so that using gamma you can make more robust algorithm with respect to the quantization error. Anyway, so we have these two step size kind of steps. One is gamma step size for the decentralized algorithm, and eta t, this is for the stochastic gradient descent algorithm. Okay, and we here the paper used stochastic approximation, and the stochastic approximation theory is proposed by Robbins and Monroe. Basically, when you have zeta t plus 1 equal to zeta n minus gamma n multiply n zeta n minus alpha update rule, here the n zeta star is equal to alpha, so the solution, as solution, the n zeta star function value equal to alpha, so that this value equal to 0. And when we're expectation of n zeta equal to so m zeta, sorry, here it is m zeta, star is equal to alpha, and n zeta is uniformly bounded, and m zeta is non-decreasing, and m prime zeta is positive, and sum of gamma n is infinity, and sum of gamma n square is bounded by some constant, then we can say that the zeta n will converge to, when n go to infinity, the zeta star. That is the stochastic approximation theory by Robbins and Monroe. So the current statement is for the scalar function case, but we can extend this theory to vector input case as well. Okay. When we have very nice step size and good control function, this control behavior will converge to the optimal solution. We can guarantee that. And here this step size is very important, and we usually say this is time and this is variance. We need to infinite time to guarantee your any initial point can convert to the optimal solution. And also you have to have finite variant so that in the end, after infinite number of iteration, you converge to the solution and never moved away from the solution. So why I introduced Robbins and Monroe? So here basically we use two time scale technique. So this gamma step size usually much bigger than this eta step size, and this gamma step size using stochastic approximation, we can guarantee that almost every time we can have averaged x value. From any starting point, when gamma is large enough compared to eta t, after sufficient number of iterations, your xt value will share almost same value among whole entry because of the Gaussian algorithm. Because of the W matrix multiplication, your old element will share almost the same value, which almost equal to the averaged value among or element. But the eta t, because the eta t is very small compared to gamma, the gradient update is very minor compared to the Gaussian algorithm update. Which means the gradient algorithm can enjoy the averaged element during this update process. So the gradient vector looks like centralized gradient. Because every server shares almost same parameter value, every server can compute the gradient at almost same point. Okay, very close point. And if the function is smooth, then gradient information can be easily combined. Okay, that is the beauty of Choco SGD. Because of the two separated timescale, the first timescale is much faster than the second timescale. And at the first timescale, we averaging the parameter values for different servers using the Gaussian algorithm. So much higher gamma value, we can achieve this. And for the second timescale, we learn the SGD algorithm. So we're using very tiny eta t value compared to gamma. We can use averaged parameter value. And then the gradient is computed under the averaged environment. A very recent paper extends this idea. So called dual accelerated method. So these two papers are very nice reference. Okay. So this paper combine Nesterov accelerated GD. So this method enhances the conversion speed. But the idea is almost the same. They also use Gaussian matrix, and they also use gradient descent approach, but they control the step size very carefully so that they can have almost the same benefit like a Nesterov accelerated GD. We already studied what is Nesterov accelerated GD, right? When we learn a momentum method with very well controlled parameters, we can speed up the convergence from 1 over kappa to 1 over square root kappa.